All right, let's rock and roll. So today I want to talk about instruction level parallelism, and we're going to look at statically scheduled processors. Embarking upon a path that is typically beyond what is covered in an undergraduate degree in computer science or computer engineering, which is to say things should get harder now. That's what you wanted to hear, I think. So here we have a representation of a 5-stage RISC processor, a fetch stage with instruction cache or instruction memory as you like, and the program counter. Interstage buffer shown as that vertical brown bar. Decode stage consisting of reading the register operands and determining the control signals for this instruction and doing the jump. Of course, we've also talked in the past about doing the branch in the decode stage. Here I've got the branch in the execute stage, the mem stage, so the data cache accesses, the write back stage, which is writing to the register file. Our ideal CPI for a pipeline is one cycle per instruction. Of course, we know that's impossible to achieve, but we can approach it by keeping the pipeline full as much as possible. It's impossible to achieve because you never start with a full pipeline. 5-stage pipeline is taking advantage of parallelism. There are 5 instructions, 5 in-flight instructions in a full pipeline in parallel. You're marching in order down this pipeline. If you increase the number of stages, then you will have more instructions in the pipeline, which means you're getting more instruction level parallelism. The ILP, assuming you're keeping that pipeline full of useful instructions. As you increase the number of stages, the goal here is to reduce the time spent in each stage, which allows you to have a higher clock frequency. You can improve performance as long as you're not losing too much CPI, right? Iron law, instruction count times CPI times clock cycle. Super pipelining is this idea of making the pipeline super deep. The drawback of having more pipeline stages, when you shrink each of those stages smaller, the interstage buffers can't shrink because they're essentially registers, can't make them any faster than they are, which means that the time to write to the interstage buffer becomes a larger portion of the clock cycle. So that's one thing to be aware of. And that's pure overhead. That's pipeline overhead. So that's the second point there about diminishing returns from the deeper pipeline, more overhead from the interstage pipeline registers. You'll have more of them too. So if you have more stages, you have more interstage buffers. The other two effects is that you need more hardware to deal with hazards. So for data hazards, more data forwarding lines, call this a bypass network, grows because every stage that can produce a value has to forward backward to every stage that might possibly consume that value. So you end up with this n times n minus 1 sort of cost. And then the control hazards. So when you have a mispredicted branch, for example, then you'll have to squash more instructions that have been incorrectly fetched into this pipeline, depending on where in the pipeline your branch gets figured out, right? As you deepen your pipeline, it gets harder and harder to have your branch earlier in your pipeline. And that's because the dominant cost at the start of your pipeline is fetching the instruction. So the Intel processor line, the x86, that was actually the x86 processor family at its height. It reached a 31-stage pipeline depth in the Pentium 4 family. The current architectures have been pretty stable around 14 stages in the x86-64 family. And that's really the extreme example of pipeline depth. RISC processors tend to have much shallower pipeline depths because they're simpler instruction sets. The other thing you can do is, instead of, or in conjunction with, making your pipeline deeper, you can make it wider. So what that means is having multiple data paths through your processor. So having multiple pipelines in one processor. The idea here is generally understood as being able to what's called issue multiple instructions in each cycle, which means that you can send more than one instruction into your pipeline each clock tick. Generally speaking, you're going to have this kind of conceptual diagram here on the bottom where you have a single fetch and a single decode stage, but they're now going to be fetching and decoding multiple instructions at a time. And then you're going to be able to issue those instructions to different pipelined units or different functional units. As an example here, 2-wide, double-wide, 5-stage pipeline has 10 instructions in flight when it's full. So it's having more instruction level parallelism going at a time. And its ideal cycles per instruction is now 0.5 because every cycle in the ideal scenario where it doesn't have any stalls or squashes, every cycle it can complete 2 instructions in the write back stage. Instead of looking at CPI below 1 as a metric for performance of these kinds of multiple issue pipelines, instructions per cycle metric is often used, which is simply the multiplicative inverse of CPI. So the ideal instructions per cycle is 2. The processor in the ideal scenario can complete 2 instructions each cycle. IPC also has the benefit of being a bigger is better metric, and humans respond well to bigger is better, monkey genetics or something. With more pipelines, we have more complexity, so the hardware cost grows. We have data hazards, so we have to consider true dependencies between the pipelines. We also have to consider write after write hazards, because the 2 instructions may write to the same destination. If you have 2 instructions moving through a pipeline together, and then at the end they both want to write to the same destination, that's a problem. You can't allow that to happen. You have to serialize those writes, or you have to fix that somehow, that problem. Of course, you want the instruction that's later in the program order, meaning think of it as you fetched 2 instructions, right? One is earlier, one is later, by definition of a program of the sequential program order. So you want the later instruction in program order to be the one who gets to write to the register file. If the later instruction in program order reads from the previous instruction's written value, then that's also a raw hazard. So you have to be able to correct that raw hazard as well. I'm using here the letter X for ALU and M for memory. So here I'm splitting execute, what we thought of traditionally as an execute stage, into a 2-stage operation here, and what we thought of as a memory stage into a 2-stage operation here, so that we can push an execute ALU instruction through the upper path and a memory load or store instruction through the lower path. So that's the idea here. Other drawbacks of having multiple issue pipelines is that when you have to stall that pipeline or squash instructions, such as in a control hazard mispredicted branch, then you're stalling or squashing twice as many instructions. If you squash what's in the fetch stage, you're squashing 2 instructions now instead of 1 instruction, which means it's costing you more, all things being equal. You also may need to add more hardware for the functional units. You may need to add more hardware, for example, in the register file. In this example, if we want to write 2 results to the register file in the same cycle, then we need to have 2 write ports in our register file, which is not something we needed in our single issue pipeline. Any questions so far? At least we're recording, so you can go back and rewatch it. So we're going to start with talking about how do you schedule instructions to execute in a multiple issue machine. Well, scheduling in general is the allocation of resources to something in time. So instruction scheduling is allocation of functional unit resources to instructions in time. Our goal for instruction scheduling is to pick instructions to go down the pipeline together in a way that avoids hazards that would cause stalls or squashes, and thereby increase how many instructions per cycle can be completed. As in many things in computer systems, there's 2 approaches, static and dynamic. Static means it's done ahead of time by the compiler, in this case. So the compiler organizes the instructions in the program, chooses the order in which those instructions will be seen by the processor, and therefore execute those instructions. Static scheduling is essentially the scheduling approach that we've been assuming all along. The compiler picks the order of the instructions and the processor fetches and executes them in that order, in program order. So then dynamic scheduling is where hardware is going to select which instructions out of a set of instructions will get to go through the processor. We're going to hold off on talking about dynamic scheduling until at least next time, if not next time. At any rate, we're going to be focusing our discussion today on static scheduling, so talking about what and how the compiler can make choices about the order of the instructions in a program in order to improve the performance on a given processor. So we're going to start by looking at a purely static scheduled approach. And I think that the best sort of segue between the RISC pipeline and a statically scheduled pipeline is to talk about this VLIW approach. So VLIW stands for very long instruction word. So what that means is that one instruction word, so what a processor fetches, is going to encode multiple instructions at a time. That's what it means. This is an approach that combines hardware modifications in order to have multiple issue processor design with compiler support to take advantage of that hardware. The compiler is going to be responsible for identifying and combining instructions into what's called a bundle or an issue packet. That's the very long instruction word that contains multiple instructions within it. So the compiler is going to put instructions into a bundle. The hardware is going to fetch a bundle, and it's going to unpack that bundle and then issue instructions to the functional units accordingly. The VLIW approach typically restricts what types of instructions can be in each location of the bundle. And we're going to look at an example, a very simple example, in just a minute to give some concreteness to this idea. It usually has a really large set of registers available, much like RISC processors do. But now we need even more registers because we have to watch out for anti-dependencies and output dependencies. We can avoid read after write hazards with better instruction scheduling. And the main one that we have to continue to avoid, just like in the RISC pipeline, is the load use hazard. I kind of wish I had actually talked about compiler approaches to avoid load use hazards before, but that's okay. Generally speaking, we'll avoid dynamic branch prediction, but that's not a rule per se. It's really a design philosophy of VLIW. The point of VLIW was to have simpler hardware and to rely on complex software, really complex compiler software, to solve hard problems ahead of time. And then EPIC is a commercial product which was developed by Hewlett-Packard and Intel. It was basically a VLIW implementation, but they added some of their own sort of quirks to the basic VLIW idea. EPIC, explicitly parallel instruction computer, created the Intel Itanium line, which you may or may not have heard of. It wasn't commercially successful. Uses the Intel IA64 instruction set, which is different than the x86-64 instruction set. We'll talk a little bit about EPIC later after we get through the basic idea of VLIW. Let's look at a VLIW MIPS 32 machine. So the idea here is that we're going to have a 2-instruction bundle with a 2-issue VLIW machine. So we'll have 64 bits in our bundle, and our bundle is going to have 2 slots. One slot for ALU or branch instructions, and the other slot for load and store instructions. So you can't put 2 R format instructions into one bundle. You can't put 2 memory instructions into one bundle. The compiler has to follow this rule. If it doesn't, then the processor will break. By break, I mean it'll raise an exception and stop fetching instructions. Bundles are fetched. Fetch addresses will be aligned to multiples of 8 bytes, because that's 64 bits. So every bundle is 8 bytes, so fetches will be 8-byte aligned. Every bundle will be aligned to an 8-byte address. And the first 4 bytes at that address will be a ALU or branch instruction, and the second 4 bytes will be a load or store instruction. If the compiler can't schedule for some reason both of those types, it will have to insert a no-op into the unused slot. For now, we're going to assume that the compiler puts independent instructions in each bundle, meaning that there's no dependencies, true, anti, or output dependencies between the ALU branch slot and the load store slot. This way, the bundle can be issued simultaneously by the hardware, and the hardware doesn't have to check for those hazards. The compiler ensures that they don't exist. The other thing that the compiler will do in our simple VLIW machine is to prevent a load use hazard between consecutive bundles. A load is finished by the end of the M2 stage. If the subsequent bundle had to read from the register that the load writes to, then we would need to forward from the write back stage back into M1 or X1 and insert a stall, a 1-cycle stall. We don't do that. The compiler avoids doing that. In this way, we don't have any dependency cross from the mem pipeline to the execute pipeline, since there's no load use hazard. I think we may still forward from our execute to our mem And we'll assume static branch prediction. We'll have to squash when that's wrong. When I stack them on top of each other like this, what this is implying is that they are going in parallel. And we're going to look at the circuitry that actually makes that happen in just a moment. There's an interstage buffer there after decode, and the outputs of that interstage buffer are going to go two places simultaneously. One place is going to be the first stage of an execute path, and the other is going to be the first stage of a memory path. Here we have it in all of its glory. It's a little complicated, but mainly the additions here are the blue lines and the blue units, light blue, kind of a turquoise-ish color, I guess. Periwinkle blue? I don't think it's quite periwinkle blue. The top, the black top part there is still our traditional execute stage with an ALU with the same kind of multiplexers, and there can be also some forwarding hardware which we've omitted. And what we can see is that the X2 stage actually doesn't do anything, or maybe it does the branch completion. The X2 is really just passing through, and the reason to have it pass through is to keep the two parallel pipelines the same length, so that they both arrive at the write back stage at the same time. We'll talk more about that in a moment. Let's look at the execute stage of the M1 path. What we've done is we've added an adder in order to calculate the effective address. So because the ALU is being used for an ALU operation, we can't use the ALU to calculate the effective address of the memory operation. And that's relatively straightforward to do, so we can do that. We duplicate some hardware in order to accomplish having these parallel pipelines. So the M1 stage is calculating the effective address. The M2 stage is doing the data memory access as usual. The write back stage, well, I should talk about the decode stage as well. We have to read from two more registers. So we have two more read indices and two more read ports in our register file so that we can feed two instructions at a time. In our write back stage, we're going to have an additional write index and write data port of our register file so that we can write the result of both an arithmetic an ALU operation and write the result of a load word operation that are in the same bundle at the same time. We would still have some additional, there'd be duplicated control logic, there'd still be some duplicated hazard detection logic, but we wouldn't need as much as we did in the 5-stage MIPS pipeline because we rely on the compiler to avoid some of those hazards from occurring. Specifically, the load use hazard can't occur, so we don't have to check for it. So here we have an example, a for loop that's been unrolled 4 times and hasn't been scheduled. This Dataflow graph shows the dependencies between instructions. 2 has a dependency on 1. The add there at line 2, it reads from T0, which the load word writes to on line 1. Compiler generates a Dataflow graph so that it can determine which instructions have dependencies on what other instructions. Dependency from 13 coming back, looping back around into 1, 4, 7, and 10. We can see that instructions 1, 4, 7, and 10 all read from T1. Actually, so do instructions 3, 6, 8, and 12. I just apparently omitted that line. That's okay for now. That's what's called a loop carried dependence. In this case, that loop carried dependence is part of the loop management code, right? Every time you unroll the loop, you have to adjust that T1. And then we've got instruction 14, which is also dependent on 13. So that's a Dataflow graph. Dataflow graph expresses the limit to which we can parallelize a chunk of code, because the dependencies imply some amount of serialization. 1 has to happen before 2, which has to happen before 3. But 1, 4, 7, and 10 can all happen at the same time because they have no dependencies with each other. Note, however, that 1 and 4, for example, have an output dependence on each other, right? They both write to T0. Right after write and right after read are name dependencies because they're dependencies in name only, the name of the register. There's no reason for can't load word into something other than T0. T5 is apparently available. Let's load word into that instead. So just picking a different name. So renaming registers is the first solution to alleviating name dependencies. And this is why RISC processors and statically scheduled processors in general have a large register set so that the compiler can allocate unused registers in order to alleviate name dependencies. Here we have an instruction schedule for the previous program on our 2-issue VLIW machine, where we've got our ALU branch slot on the left and our load word, store word slot on the right. And we have to avoid load use hazards. In cycle 0 there, we're going to load word into T0. We've got to wait until cycle 2 before we can read from T0. That's what it means to avoid a load use hazard, because it takes 2 cycles to finish a load. And so we won't have the value in the write back stage until 2 cycles after that load begins in the mem1 stage. Let's see, what else is worth saying here? We can't branch before that store word at the end is done, because if we can't move the branch up because we don't want to branch before the store word happens. We can move the adds down if we wanted to, but it doesn't really help anything, right? So we have 1, 2, 3. We have 6 ALU and branch instructions, and we have 8 loads and stores instructions. So no matter what we do, we're going to have 2 no-ops somewhere. Another thing worth noting is cycle 0, we've moved the loop maintenance code to the very beginning of the loop, which is going to help us to avoid a raw dependency between add and branch, which is fine. I mean, it doesn't really matter. I don't think it matters. I have to remember. But as a result, the load word there is going to read from the old value of T1. The load word in cycle 0 reads from the old value of T1 because there's no forwarding logic. So the compiler is abusing this requirement that instructions be independent, because you can see, it doesn't look like those 2 instructions are independent, right? The load word is reading from T1 and the add I is writing to T1. So just by looking at it, we think there's a raw hazard. But the compiler knows that the processor is not going to check for that. The load word is going to read the old value of T1, and that's what the compiler wants to happen. But then notice that the next line, load word T5, is now going to offset 12 from T1. This is actually -4. And this corresponds with here, line 4, load word T0, -4 of T1. So we move the add I of T1 minus 16 to the start of the loop, and then we add 16 to all of the following displacements or offsets. And then we use different names. We're using T5 and T6 so that we can issue multiple loads before we use their results. So we're going to load word into T5 instead of T0 and load word into T6 instead of T0 because we need to keep T0 around until we use it in the add in cycle 2. So the compiler decides all of this, mostly operating on graphs and trees, in order to assign instructions into these bundles, and then the empty bundle slots will get no ops put in them. By analysis, we can see that there's 14 instructions and we finished them in 8 cycles, and so we've got an IPC of 1.75. If we had executed this loop in a 5-stage risk pipeline, we would have gotten 0.74 IPC. From that, we could calculate our speed up if we were so inclined. VLIW is nice. The hardware is relatively simple, which makes it a little easier to understand, I think, as a transition point here. We do have to get to understand a little bit about what a compiler does in order to understand how this works. As we want to squeeze more performance, we've got to make the compiler more and more complicated. And we have to make the compiler work together with the hardware a lot more. And so compiler design and implementation actually becomes one of the dominant costs for these types of machines. Compiler optimization for VLIW machines was a huge deal when VLIW was introduced. It really motivated a lot of research into compiler design and really moved forward compilers on the whole. VLIW has a major drawback, which is that if you change anything about the hardware, the binaries need to be recompiled. If you add another slot to every bundle, your old bundles are no longer valid. Another problem is that the code size grows. We had to add no ops when we couldn't schedule useful instructions. So we actually had a larger code size. Although we were able to execute it faster, it is wasteful of space in that way. It's also a little wasteful of execution time by having those unused slots. So we're getting things done faster, but we're using more resources to do that. And so there's a trade-off that we're making. Historically, computer system designers were happy to make that trade-off because speed is king. However, over time, power and other financial costs became more important. Advanced techniques in VLIW machines to deal with control hazards and with long memory access times, specifically load speculation and a technique known as predication, which we'll cover briefly, are also wasteful. They end up leading to squashing instructions when they're wrong or simply discarding their results. Lockstep execution of a bundle moving down the pipeline in tandem means that when you have a stall in one part of the bundle, you have to stall all of the bundle. So you stall everything, which makes it harder to hide cache misses, for example. If you have a load instruction in a bundle with an add instruction, and that load has a cache miss, then you have to stall until you get the data for that load. And that means you also are stalling the ALU pipeline. And then the instruction alignment can also lead to waste because instructions have to be aligned to the bundle size. That means every basic block that is a branch target has to also be aligned to the bundle size, which means you may have to add no ops perhaps. Load speculation is an assumption by the compiler that if you store something and then you load something, those are going to be two different addresses. In general, the compiler can't determine this ahead of time. The two instructions could be calculating their effective address from two different registers that have the same value, but the compiler may not be able to determine that. You don't know that until runtime, then the hardware can determine that they had the same value. So this problem of determining if two addresses are the same is something known as memory disambiguation, which is that you don't know that effective address of a load or a store instruction until the end of the M1 stage when you calculate it. So in the program, we have a store followed by a load. The compiler is going to assume that the store and the load are to different locations. If they're to the same location, that means that the load should get what that store stores. So I store to A, I load from A, I better get A. Now, If I assume that I'm storing to A and I'm loading from B, then I can move that load before the store because they're independent of each other. And I want to do that because loads are in the critical path of the data flow graph of my program. And so I want to get that load done as soon as I can so that I can execute the dependent instructions sooner. If the compiler does this load speculation, but it does it wrong, it misspeculates, turns out that actually A and B are the same address, then we actually loaded the wrong value because we should have loaded whatever the store stores. The way this is handled is allow the compiler to do load speculation, but then detect it either using additional code known as compensation code. So we check later if they were in fact the same address using some kind of branch or conditional instruction, and then fix them up. Or we can add some hardware support in the M1 stage to detect that two instructions had the same effective address. The hardware approach only works if the load and store are close enough in time that the hardware can actually detect it. Compiler compensation code approach can work in general because the compiler can arbitrarily go back in time to remember what it did. This is alluding to a problem we're going to face in general, which is this memory disambiguation. So hopefully at least that part made sense. Branches are really bad for VLIW machines because consider our MIPS VLIW machine. If the branch is resolved in X1, then we have to squash, fetch, and decode, which means we've got 2 stages worth of 2-issue window to squash. So we're paying a much steeper penalty than we paid in a RISC pipeline for mispredicted branches. Dynamic branch prediction could be used. It could be helpful. We've talked about how to do dynamic branch prediction before. The cost of that is we have to add hardware. It goes against the VLIW philosophy of put the complexity in the compiler, but it's doable. An alternative, which was interesting at the time but turned out to not be all that useful, is known as predication, coming from the root word predicate. So Boolean predicate, meaning something that's true or false. So the idea is we use a predicate, sometimes these are known as conditional codes, to determine whether we will actually allow an instruction to commit its result to the state of the processor. So commit is a new term we're going to use quite frequently in the future. So commit is allowing an instruction to finish a store to memory or to finish a write back to the register file. That's what it means to commit. If we add predication, predicate bits to every instruction, that means we're increasing our instruction size. We have to make this decision ahead of time because we're modifying the instruction issue packet size, and we've got to have hardware to deal with these predicates, and our compiler has to be able to generate these conditional instructions. The benefit of these condition codes or predicates is that we can make instructions predicated on the outcome of previous instructions that set the condition codes. And as a result, we can convert branches into predicate assignments and then use those predicates on instructions that are controlled by the branch. So think about an if statement where you would normally branch past if the condition is false and fall through if it's true. What you can do is you can set a predicate based on the condition of the conditional statement of the if, and then you use that predicate so that if that predicate is true, the instructions inside the if block commit. And if the predicate is false, they won't commit. So now what you do is you fetch and execute the instructions in the if block, in the conditional block, and they have this predicate bit attached to them. And you check the predicate just before you would do the the commit, the write back, or the store to memory. And if the predicate is false, then you'll squash those instructions at that point in time. You end up fetching and squashing all the instructions that you would normally branch over when the condition is false. The x86 instruction set has some limited conditional instructions. Now that's cmove if equal. Fully predicated machines were kind of explored, especially in the design of the EPIC Itanium instruction set. So now you always squash, but you never have to stall. In general, the performance ended up being not that great for the cost you end up having to pay, which is fetching all instructions and executing them, regardless of whether you want to keep the result or not. You end up wasting a lot of work because you end up discarding what you do. So that's predication in a nutshell. Let's do a hypothetical here. What if we want to add a floating point multiply accumulate unit? So FMAC, floating point multiply and accumulate. And suppose this floating point unit requires 3 cycles to finish. That means we would need 3 stages for our floating point unit. We have to extend our bundle size by 1 more instruction to encode our floating point operation. And we also have to increase the pipeline depth so that all of our instruction types have the same depth of pipeline stage so that the bundle can move through the pipeline synchronously. So our machine is no longer backward compatible. Pretty hard to make a backward compatible machine when you add a floating point instruction to the instruction set in general. We're going to have to add a floating point register file for our floating point operation. That's fine. It'll be helpful if we do a lot of floating point operations. We're going to get the most benefit if we have a good balance of execute branch, load store, and floating point operations. If they're not well balanced, then the compiler is going to have a hard time maximizing the instruction schedule, and we'll end up with a lot of no-ops in our schedule. One way to help alleviate those last 2 problems, extending the packet size and finding instructions to fill up every packet, is to allow multiple types of issue packets. So maybe we have traditional ALU branch and load store packet, and then we have another ALU branch and floating point operation packet. In this case, if we have just 2, then we can use a single bit to discriminate between them. And then we can add some hardware in our decode stage, or between our decode stage and the first stage of our pipeline, really, to do what's called instruction steering, which is to direct each individual instruction to the pipeline that it should go down, and to insert a no-op into the unused pipeline. So if I fetch a issue packet of type 1, when I decode it, I'm going to read that bit, and it's going to tell me that there's an ALU branch instruction and there's a floating point instruction. And so I'm going to steer the ALU branch instruction up to the X1 pipeline, and I'm going to steer the floating point instruction down to the FP1 pipeline, and I'm going to inject a no-op into the M pipeline. The hardware is providing some of this instruction steering, and the compiler is assigning those so-called template bits. The template tells the hardware which issue packet template it used to put the instructions into the issue packet. So that can help, but it also means you can't push all 3 instructions into the pipeline at the same time. So usually this instruction steering could be done by adding what's called an issue stage between the decode stage and the functional unit pipelines. We're going to use the issue stage to also read from the register operands. So now decode is simply focused on unpacking the bundle and maybe doing a little bit of the control logic. So we can do this issue logic instruction steering with our example here. The first instruction in both of the templates is always an ALU branch pipeline, so it's actually a trivial steering. We always send the first instruction into the ALU branch pipeline. And then we take the second instruction and we check if our template bit tells us that this is a memory, then we can send it to the memory pipeline. If it tells us that it's a floating point operation, we can send it to the floating point operation. Now, we don't actually need the template bit to tell us that if we have access to the opcode in the instruction. So in that case, we could use the opcode to steer the instruction as well, and then we can remove template bits from our instruction, from our issue packet rather. If we further duplicate this logic and we extend it to check the opcodes for loads and stores and the opcodes for floating point operations, then we can allow either slot to have any of the instruction types, and we can steer any instruction in any slot to the right pipeline, as long as the compiler doesn't allow multiple instructions of the same type in the issue packet. We still can't have two ALU branch instructions in the same issue packet. We can't have two mem instructions in the same issue packet because we only have one of each of those pipelines. So we're still going to statically schedule our instructions in order to avoid hazards, but we can use this steering logic to pick where in the hardware it goes. We can simplify our compiler by adding hazard detection logic in our issue stage, can check for dependencies between instructions within the same issue packet. And that would allow the compiler to schedule instructions together that might have stalls. The compiler can still avoid stalls it knows will happen, so it can still avoid load use stalls within a single issue packet. And the compiler could add some hints to the bundle to help the hardware to do hazard detection. All of this has been explored before. That's the extent to which I really want to talk about it today. But at this point, with issue stage and hazard detection logic, we have the ability to fetch any sequential batch of the instruction window number of instructions, whether that's 2 in our example or 4 or whatever. We can have arbitrary instruction alignment. We no longer need to align to a bundle size. If we don't need any of those issue packet bits to give hints to the hardware, then we can fetch arbitrary instructions in the program. If the instructions are arbitrarily aligned, we may have some complexity in the instruction cache, but that's beyond the scope of this class. And we also may have some complexity in the branch prediction hardware in the fetch stage, but that's maybe a topic for later. And we need a lot more hazard detection logic than we needed in the risk pipeline. Like I was talking about before, the hazard detection logic grows. It's in the square of the width of the length of the pipeline, so the number of stages. And the forwarding network also grows in that dimension as well. So this is right here a good place for us to stop. This is a static superscalar processor. So it's statically scheduled. The compiler is still picking the order of instructions and how they're going to go down the pipeline together. The hardware is issuing multiple instructions at a time, subtly different from VLIW because we don't have this notion of an issue packet. And we're going to continue on from this point of static superscalar and really get into the weeds quite a bit more. Before we go, I just want to come back and circle around to the EPIC Itanium processor, colloquially, jocularly called the Itanic. It's clever. There are about 7 generations of Itanium processors from 2001 to 2021. So when I say it wasn't commercially successful, it had limited success, but really they just kept on producing it. I'm not even sure if they were making money off of it. It was popular in some servers. It was announced end of life at the beginning of before COVID. It has these features: 128-bit bundle size with 3 instructions. So each instruction is 41 bits, and it uses a 5-bit template to give a hint to the hardware of what the issue packet is. So the template encodes the types of instructions, and it also does provide some hints about dependencies within the packet. It's got these stop bits in the template that allow you to have that allow some level of forward compatibility to future generations of the Itanium. It has a large register file, 128 general purpose registers, 128 floating point registers, and 64 predicate registers, I think they were. Predicate, I don't remember how wide each predicate register is, though. It has full predication, so every instruction can be predicated. It has dynamic branch prediction, and it also has hardware prefetching. It has a queue to decouple fetching and decoding, so you can fetch, and fill up an instruction queue while you're decoding them. It uses a non-blocking cache, and it has 10 stages and 9 functional units, 2 ALU pipelines, 2 that can be ALU or load store pipelines. The load store, the memory pipelines have a full ALU for doing their effective address calculation, which allows those pipelines to handle either ALU or load store instructions. It has 2 floating point multiply accumulate pipelines and 3 branch pipelines or functional units. I3O is shorthand for in order fetch, in order issue, in order execute, out of order write back, I think, if I remember right, my shorthand there. And it deals with many of the dependencies by predicates. It does have a scoreboard, and that's what we're going to talk about next week is scoreboarding. So it's it ended up being a very complex hardware processor design and a very complex compiler design. And for this reason, and that's one of the main reasons it never really achieved widespread adoption. Well, we'll talk a little bit about static superscalar and scoreboarding next week as our segue into dynamic superscalar. Static scheduling relies heavily on the compiler to squeeze performance out of the processor. Oftentimes there is some interaction, some kind of interface between the compiler and the hardware so that they can work together. 2 extremes of the static scheduled multiple issue processor are sort of this purist VLIW and then a static superscalar, which we'll talk about more next time. And EPIC is somewhere in the middle and seems to have the worst of all worlds. It moved forward a lot in both compiler and actually computer architecture research. That's the end of today's talk. We'll pick up with static superscalar next. We'll see how that goes. Dense stuff. I know that was a lot, but probably less than usual, actually.